Sorry for the poor mic quality and lack of uploads. I don't know what I'm gonna do first, but whatever. I want to actually do something, and I'm pretty sure you saw by the title, that a lot of people don't really understand because a lot of math videos suck at explaining it, I think, and they don't really explain it in a very sufficient way, right? Yes, I look retarded. But yeah, a lot of E to the pi I videos really glorify it and say, ooh, -1. They either fucking do this shit.
It is actually the most beautiful equation in math.
And just fucking put a bunch of numbers and say, oh yeah, this works and stuff, and people just agree, oh, okay, yeah, I guess because he said so, it works, so, big brain. And I don't know why they fucking post those videos, because some people actually do want to understand this packet, and he's like, oh, I'm so excited about it, but he doesn't explain it and stuff. Many people are introduced to this, because this is very famous. This is actually, I'm pretty sure this is Euler's formula. This isn't Euler's identity, like this kind of says. This actually requires calculus. It's pretty easy if you know Taylor series, but I'm assuming you don't, because most of these people that watch the videos are normies. Yes, I use that word. But yeah, I want to try to do this, right? So, what is Taylor series, right? Well, Taylor series is looking at any function, not non-polynomial function, right? And producing it as a polynomial function, x to the n plus some constant times x to the n minus 1, etc., right? Plus a constant, right? You may be saying, oh, that actually does sound interesting, and it's, well, should sound pretty doable. It is actually very doable and very simple, right? Just takes a lot of intuition and grinding, right? So what is Taylor series, right? I already explained that. I'm going to reiterate myself. So, how do we find this, right? How do we find a polynomial version of this that that kind of sticks to it? You know, that kind of, like, say, so sorry for the lack of quality in this. So e to the x is 1. E to the x kind of looks like this, right? This is kind of what it looks like. So we're trying to find a polynomial function that kind of looks like this, that kind of spoon feeds it, right? This would be kind of like what the polynomial function looks like. And as we get more and more accurate, if we go to the third power, right, it's going to kind of look like this. Then we go to the other power, and it's going to slowly kind of spoon it, right? It's gonna touch it, and eventually the polynomial will be so big that it will just, it'll just be completely exact. And we have to actually use infinite sums of polynomials, right? Imagine it, right? So if this is kind of accurate, so say we have 1, right? Say we start off with 1, right? It touches 1. It touches the point at 1, so it kind of touches it, right? We already have that point, and it has to touch a certain point, right? At 0, it touches 1. So now we have our first constant, 1 plus what? So now we have another constant we have to deal with. C1, no, C2, this is the second constant, times the next value, right? And then we have to add another constant. We have to add C3 times x. So let's start small, right? One way you can actually do this is using derivatives. Instead of constantly changing the constant to kind of on Desmos to see a polynomial that will fit in it, we can use derivatives, right? What is a derivative? A derivative of a function of x, right, is equal to the, well, it's usually the equation to find a slope at a point, right? So if you find f prime at a, this is equal to the slope of that point, right? So it's equal to, so say we have x squared, right? We find the derivative of x squared, right? And we're kind of finding the slope at any point. We can find it at any point. We just need to plug in a certain number, right? So how do we find this, right? What is that slope formula actually? Well, the slope formula is equal to some value of y minus another value of y over one value of x minus another value of x, right? So that's great. So we can kind of find a formula, right? So for that, right? So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. So x squared, we can plot this down. This is 0, 0, 0, 0. 1, it's 1. 2, it is 4. 3, it is, I can't see the 9. 4, 5, 6, 7, 8, 9. Right about here. At 4, well, that's the highest thing I could do, right? And it has this kind of symmetric property since it's x squared, right? So if it's the negative side, if you put a negative value for x, right, it's just going to square it, and it's just going to be x squared. So it's the same exact thing from both sides. So it's kind of going to look like this, right? That's kind of how it looks like. So right, how do we find a slope at one point? If we're just estimating the slope, right? Well, say we want to find the slope around 1. We want to find the slope at 1, right? No, actually, we want to find the slope at 2. 2. 2 is a good estimate, right? So, how do we find this? Well, we can actually estimate it by finding the slope of the 2 points around it, right? And you see how it kind of touches it, right? So what's the slope of the 2 lines around? So we have a difference. This is called difference, or a change in a, what else is it called? Displacement of, sorry, that took so long. Displacement of x would be equal to, well, the difference from the two x values is 1 and 2, so that's just 2, right? On the displacement of the y values, right? What's the difference, right? It's 1. It's from 1, and that goes to 9. So that's is equal to 9 minus 1. So that's equal to 8 over 2. So 4 is equal to the slope of that line at that point, right? So we can only find an estimate right now. So how do we find a slope at that exact point, right? Well, if you actually notice, right, if you slowly close on in the displacement of x, right, and you slowly go in, you notice that it actually kind of hits that tangency line, right? So one way we can write this is the limit as a limit, right? The limit as x approaches that constant, right? So we want to find the limit as x approaches 2 of f of x minus f of 2 over x minus 2. And we wrote the slope formula, right? So if we plug this in, x of 2, right? What is that? F of x, actually, first of all, that would be limit as x approaches 2 of x squared minus 4 over x minus 2. And what can we simplify this to? Well, we can actually simplify this to x. Well, we can actually, well, okay, we can divide this by x minus 2, and we get x plus 2. If you don't know how to factor, then maybe you should learn that, because that's algebra 2. And I have no idea why you'd be interested into E if you're in algebra. I mean, it's algebra 1, not algebra 2. This is trivial. The limit is x approaches 2, so now we can actually find something, because if we actually plugged in x is 2, this would just be 0 over 0. But that's not possible, right? So we find a limit. Well, first we evaluate this function, and it may seem like cheating, but it's not. It's just a hidden mine, right? Just a hidden attribute. So now we plug in 2, and that is equal to 4. Well, what do you know? That is actually just 4x, right? So 4x is equal to the slope, but we haven't found the line, right? The line tangent to it, right? Because not only do we have to find the slope, but we also have to find the y-intercept to actually hit that point. So what do we do here? Well, we do y is equal to f of x, 4x plus b, right? So if it has to touch that line, right, and we're trying to find b, then therefore at x is equal to 2, right? We just plug in x is equal to 2 from that equation, right? So f of 2 is equal to 4, right? It has to touch that point. It has to touch that point. So these parameters depend on 4 being equal to 8 plus b. So if we use arithmetic, -4 is equal to b. So the equation of the line tangent to x squared at 2 is equal to y is equal to 4x minus 4. If we plug in 2, that's 8 minus 4, and what do you know? It hits 4, right? And if you want more proof of this trickery, I will not show you what I may or may not be. Oh yeah. Right. So we plug in it to desmos.com. This is a very good calculating thing. Graphing thing. Or the graphing thing is just plugs in. It tells the computer to plug in stuff, so it's reliable. We have x squared. There we go. That's the actual x squared in our graph. Now we plug in 4x minus 4. What do you know? It hits that point right. It touches that point right there, right? So now that's what a derivative is, right? So, well, this does work, right? This form does work. But what if we have the derivative of e to the x, right? What is f prime of x, right? What is that equal to, right? Well, you could say we just plug in e to the x, right, at a point, at any point, right? Say we want to find 0 minus e to the x approaches 0, e to the 0, or x minus 0, which is just 0. So this is equal to e to the x minus 1 over x is limit as x approaches 0, right? That is a very nice formula. But we can't find this, can we? We can't plug it in. We can't find a limit, right? But if we tried, we could find 0, 0, 0, 0, 0, 1, right? So that's a really small number, right? Divided by, well, just some number, which is equal to infinity? No. What we have to use here is the other form of derivative, right? If the derivative of a function with respect to x is equal to the slope of f(x), any point, right? Well, can we also use this, right? The limit, right? So, can we also use this definition, right? So, if slope is y2 minus y1 over x2 minus x1, what is y2? What is x1? x2. What is x2? Well, x2 is actually just x1 plus a difference in x, right? It's plus a difference in x, right? Does that make sense? X2 is just a different point on the graph, and it is adding the original x value by a difference in x. It could be negative, it could be positive, but it's just a difference in x. You don't know what the difference of x is, we just know that it is a length, right? It is a distance from x. So, we can rewrite this whole thing into f of x plus difference in x minus f of x over x plus the difference in x minus x, and this just cancels out, and this becomes f of x plus a difference in x minus f of x, sorry for the clicking, over delta x. And we're trying to find one thing, right? We're trying to find as f of x plus the difference in x approaches 0, so they're the same thing. So this is just the limit as the difference in x, or delta x, it's the Greek terms, delta x approaches 0, is equal to the derivative of f of x over dx. Great. So now we have a formal definition of a derivative. We can find it at any point. Once we find the derivative of function, right? We find the equation of the derivative of function, right? So we find that equation, right? And then we can plug it in at any point and we get the slope. So let's try this again. Derivative of e to the x over x with respect to x is equal to the limit as delta x approaches 0 of e to the x plus difference in x minus e to the x over difference in x, right? So you can simplify this into the limit of delta x approaches 0. And because we use, I don't know what the rule is, but we know that an exponent raised to the power plus another power is equal to that exponent to the power times a to the power, right? Which is e to the x, e to the delta x, minus e to the x over delta x. Now we still got a messy equation here, but we can notice one thing. E to the x is being multiplied by 2. You can simplify this and remove e to the x outside, so that's limit as delta x approaches 0 of e to the x times e to the delta x minus 1 over delta x. And we notice we're only trying to find the limit as delta x approaches 0. So we can kind of treat this as a constant or a number just like 2, 4, 5, because once you find this limit, right, we're just multiplying it by that. So we can move this outside the equation and get e to the x limit as delta x approaches 0 of e to the delta x minus 1 over delta x. And still got the original equation we got before. Do not fret. We can actually simplify this, right? I lied to you about the inability to actually solve this. This is actually very you can actually solve this. I had a smirk on my face when saying it. Could solve this, and I don't know if you can find the what do I call it? What is this? Desmos on Google. Desmos. E to the x minus 1 over x. That is phenomenal. Yeah, so let's imagine e to the delta x minus 1 is e to the x minus 1, right? So what we're doing here is we're translating it downwards. So e to the x minus 1. We're subtracting the y value of x minus 1. So e to the 0 minus 1 is just equal to 0, right? But now we're dividing it by an extra x value, right? So we're dividing it by an extra x value. So now we're not only manipulating the equation by arithmetic, but now we're manipulating the y value by a certain value, right? I mean, a certain, we're dividing it, right? We're dividing it by x value. The same x value we're dividing e to the x. So we can do e to the x over x minus 1 over x, right? Alright, so this still looks pretty messy. So what's e to the x over x? Let's do e to the x over x. Well, it is not a continuous function. So what we're going to have to do here is just, is there a better way to do this? I always use intuition, which is a fucking gateway. E to the x minus 1. Oh, you have to use 10 of this series. Okay. So how do you do this? Well, there's 3 ways. There's a couple ways to do limits, right? You can either use intuition, which means just plugging it in continuously, plug it in the value 2.01 negative 1.99, and you're approaching 1.99, and we're approaching 2, right? So we just plug in values close to it, because the limit isn't, we're not finding the value at that point, we're finding everything near it, right? Or you can also just use factoring, trig rules and stuff. So in this case, without my handy stuff that I'm trying to teach you, you can only use intuition, right? So let's plug in 0.01 to that equation, right? 0.01 minus 1 over 0.01, and it doesn't really matter if it's negative. E to the 0.01. So that is approximately 1 point blah, blah, blah. We subtract that by 1, and we divide it by 0.01, and then we get 1.005, right? Now we increase that to e to the 0.00001 minus 1 over 0.00001. You'll see that value. 0.00001 e to that value minus 1 divided by 0.00001. And we notice how it kind of looks like the original value of e to the 0.01, right? We're just increasing the digits from 0. And if we continue doing this, then this becomes 0.0000000 time plus a bunch of additional constants. So we can just say, and we also have to do the from the left. Whatever. 0.00001 copy. We can't just assume that it's gonna straight from the right, because limit stuff. You don't really know this. So that's right. Okay, whatever. Minus 1 divided by alright, so from the left, right, so the limit from the right, so the limit as delta x approaches 0 from the right side of 0 of e to the delta x minus 1 over delta x is equal to 1.0 something times and a constant, right? The limit from as delta x approaches 0 from the left of e to the delta x minus 1 over delta x is equal to 0.9 repeating and some other constants, right? So the limit from the left of 0 and the limit from the right of 0 both converge to 1. They may not have the same ways of converging, but they still converge to 1. So we can say this is just 1, right? That's a nice little special property of e. This is just equal to 1, and that means the derivative of e to the x is equal to e to the x. So that is amazing, because if we want to find the second derivative of e to the x, that's just going to be e to the x, right? If the derivative, it's just the same function continuously, right? And then if we want to find the integral of e to the x, or the antiderivative of e to the x, that's just e to the x, because the derivative of e to the x is equal to e to the x. So that's its derivative. So we want to cancel this out, and then it's just e to the x. So it's amazing. It's a nice little property of e to the x, which makes differentiation a lot easier using that as a frame of reference. It's crazy how geniuses come up with this. Back to the original question, right? We want to find a polynomial. And how does this relate to this, right? Taylor series and Taylor series basically. That's what I'm gonna tell you, right? So now we know that 1 plus, okay, I'm tired.